feedback nonsense. Okay. Okay. Rock and
I
roll.
also figured out that when you live stream and clicks over to YouTube, if you don't close down that page on YouTube, it's yeah, you hear like an echo. It's pretty amazing. Okay. All right. Hi everybody. Can you guys hear me? Oh, hang on a second. Sounds yeah.
Oh, I wonder if I have to put my audio out through the HDMI.
I can hear you.
Let me send it out through the HDMI. Okay, talk again. It's all over there now. So.
Let's see.
Can y'all hear us?
Yeah, I can hear you.
You're coming through here.
No, I thought it was here.
No, because the speakers are up here.
Oh,
We would definitely heard it. Let's see.
but it says it's going out through the HDMI now, right? So I'm sending it out to the HDMI.
Yeah.
So it's not coming through my speakers. It's going to there, but it's
Where did
not
it
going
come
to
from?
the room.
Yeah.
I thought I heard it right here.
Let's see. Yeah, so let me do this. All right. Hey, let me go over here.
Yeah.
Tim's this with me.
Testing. Can you hear me?
So we're trying to get it to Travis, right? You saw.
Yeah, I can hear you.
I can hear you.
No, it's coming here. It's still coming here. It's not going out to the HDMI, even though it says it is.
Yeah.
Nicole couldn't.
Play sound through. Try it again.
It might be a setting in Zoom,
Well, that's oh, I
like
see.
in Zoom
In
itself.
audio. Ah, okay. Now try it. Okay, I think that's it.
Let's see. Can you guys talk one more time online?
Yeah, I can hear you both.
Perfect. Rock and roll.
All right, we'll go ahead and let Dr. Larson start up. Hi, everybody. Welcome to the October flavor of BSAS's member meeting. Thank you for postponing for a day for us so we could fit everybody in and get the scheduling worked out with the observatory. We're really excited to have Dr. Larson with us today. He's talked to us a couple times in person, a couple times online. I love listening to him talk. I heard him first at West Virginia Star Party.
Okay.
And so ever since then, I've been kind of a fan of him. So I'm glad to have him here. He's expanding on one of his talks. You can find a shorter version online of a TED Talk here. And so hopefully you guys will get a lot out of this. So, all right, Dr. Larson.
Okay, rock and roll. Well, thank you, everyone. I appreciate hosting, and I'm a professional astronomer as well as an amateur astronomer. So I always love coming and talking to amateurs because it's stuff that's near and dear to my heart professionally, but it's folks that I hang out with and are near and dear to my heart anyways. The problem for all of you all, because I am an amateur and a professional, is sometimes I'll say we, and I mean we the amateurs, and sometimes I'll say we and mean we the professionals, and y'all will have to just figure out which one it is, because I don't always tell you which one I'm talking about. So that's the only thing to be aware of. I am currently at Clarkson University, which is in Northern New York. I been at Northwestern for about 15 years, 12 years, something like that. My wife is also an astronomer. She was formerly the president of the Adler Planetarium in Chicago. She is now the president of Clarkson University, which is why we moved to Northern New York. So we're both amateur astronomers as well as professional astronomers. So she does these things sometimes as well. But we just recently moved to Northern New York. We live right outside the Adirondack Park. So if you go look at the dark sky map, it is far better dark skies there than it is in Chicago, which is excellent. So I have a 22-inch Dob, and it is getting a little more used than it was in Chicago, which is great. So anyways, it's a technical school. We do mostly STEM degrees. So if you have young people who are interested in going into engineering or sciences, or if you're tired of being a 7-Eleven manager, lawyer, long-haul trucker, whatever you are, you want to go back to school, you come on up to Clarkson and we'll get you all set up. Okay. Okay. We're going to talk tonight about kind of thinking about our place in the cosmos. This, as Tom said, I did this talk a long time ago for TEDx. So there's kind of a 10-minute version of it. And so this is kind of a little bit longer. If you want to kind of remind yourself of it or you want to kind of go back and see it again, you can certainly find the TEDx on YouTube. So if you just Google finding feeling small in a big cosmos, you'll find it. Okay. Okay. We'll take questions as we go. I'll try not to talk more than an hour or so. I normally do okay, unless we take too many questions. If questions get out of hand in the middle, I'll try and contain them, right? And then we'll take questions at the end. But I don't have any place else to be tonight. So if you want to talk more afterwards, I'm certainly happy to take questions as long as folks want to. Okay. But what will happen, and most of you know this by this point in your lives, is about 2 weeks from now, you'll wake up at 2 in the morning and you'll be like, oh, I wished I had asked that question. Okay. And if you haven't learned yet, you will learn that your significant other doesn't want to talk about astrophysics at 2 in the morning. Okay. And so when that happens, you can send me an email. So my email address is right there. And I will do my best to find you a YouTube video, give you a book to read, send you to a blog post, something to answer your question if I can't answer it. Okay. That's my blog right there, rightscience.wordpress.com. It is a public facing blog. It's really there so my parents know what I do because my mom's a forester and my dad's a plant ecologist, so astronomy is pretty far from their world. But there's all kinds of stuff there about alien life and black holes and gravitational waves and cosmology, just whatever strikes my fancy that week when I read. So you may find some stuff there. I think there's a few posts that are based on this talk there as well, so you can go read about this if you want to. Okay, and you can certainly follow me on social media there if you want to. Okay. So as astronomers, we are used to thinking about questions that melt people's brains a lot. Why are we here? Where did the universe come from? What are the limits of it? What's its long-term future? What is its infinite past? And we're kind of used to kind of talking about those questions because we talk about them all the time. And we talk about them so often that I think we kind of forget that kind of brain melting aspect that those questions have the first time we ponder those questions. And many of you have probably experienced this when someone comes up to your telescope at night and you show them something, they're like, how far away is it, right? And you're like, oh, that's 27,000 light years away, right? It's like, wow, the cosmos is so big. And of course, 27,000 light years is not that far at all, right? The cosmos is far vaster. And so what I want to do tonight is go back to those early moments when you were first learning about the universe and just remember what it was like to think about how big we are in this impossibly large universe that we're in. And that's kind of good fodder for philosophical, keep you up all night kind of thinking. But it's also good fodder for really thinking about the perspective we should have about what we can accomplish as a species. Okay, and so that's really the framework that I want the conversation to be in. And I think those are good things for us to remember when we are in trying times as we are, and it feels like some days that the world's just never going to get better, but it can get better because we have the ability to make it better. And that's really the ethos that I want to project to y'all tonight. Okay, and that's the power that astronomy has to teach us. So I grew up in this because I saw Carl Sagan at the right age, right? So Cosmos came out when I was in 6th grade. And I watched it fastidiously, right, every week. And so when I teach astronomy as a professor, when I do public lectures, it's Carl's voice I hear in my head all the time still, right? And so the reason I do stuff like this is because, well, that's what professional astronomers do. Carl Sagan was the first professional astronomer I knew, so clearly I should do what Carl Sagan does, right? Okay, so I always open this talk with this quote from Carl, which many of you may recognize. It's from the opening scene of Cosmos. And he says, the size and age of the cosmos are beyond ordinary human understanding. Okay, lost somewhere between immensity and eternity is our tiny planetary home, the Earth. And one of the things that I've always valued about Carl Sagan, and one of the things that I think we forget, particularly those of us who do professional science, is the value of accepting that the only way to talk about the things you and I think about all the time is to use the power of language, the poetry of language, if you will, to talk about how tremendous a change, how tremendous an effect the universe can have on this person. Okay, and so I always go back to this beginning. And most people, no one in Chicago has ever seen this, but most of y'all have, right? So this is the Milky Way over the Grand Tetons, where I grew up in the Rockies. And so this is kind of, the thing you have. So the beginning, the shores of the cosmic ocean, as Sagan called it, is the Earth. And this picture is a picture that is singularly unique to the moment in time that you and I lived. And many of you are my age or older, so we grew up during the space age, okay? But those of you who are older than me, right, there was a time before we ever flew to the moon where we did not have this kind of picture of the Earth. We imagined what this picture of the Earth looked like, but we had never seen the Earth this way until the Apollo astronauts flew to the moon. Okay? This picture, our understanding that this is what our world looks like, is less than 60 years old. And even though I can put this picture up and all of us recognize it, it has a name, it's called the blue marble. This is what NASA calls it, right? Even though I can do that, there are only 24 people in the history of the human race who have seen this picture with their own eyes. That's amazing, right? But what's remarkable about that is we are so good as a species at delivering as common knowledge from NASA to the astronauts to me and you, that there's no person on this planet, virtually no one on this planet, who doesn't recognize this picture when I put it up. Our species has grown to the point where it is common accepted knowledge that we know what our planet looks like from space, even though none of us has ever been there. I assume none of you are Apollo astronauts. So. Yeah, right. Not yet. Any Artemis astronauts in the audience? No? Okay. Soon to be. Okay. So it does get better than this. So what is this? This is the Hubble Space Telescope. Yeah, right. Sorry, I've never given a lecture under the Hubble Space Telescope. Okay, that is awesome. Right. Okay. So Hubble is arguably the most successful scientific instrument in history. Okay, it has seen farther and has discovered more than any scientific experiment, facility, anything that we have ever built. There have been some 15,000 papers written about Hubble's discoveries, and it's still going. Okay, because it's so useful. We just, right? We should deorbit it, right? We need to spend the money on different telescopes, but Hubble is the backbone of modern astronomy. And when you see pictures in magazines and Sky and Telescope and astronomy textbooks, almost all of those pictures of outer space that you and I have grown up looking at came from this instrument. There's a few from Palomar, and now there's ones from JWST. But the pictures that stick in your mind, the ones that you're like, oh, right, those came from Hubble. Okay. Now, when we decided to build Hubble, okay, so astronomers get together every 10 years and they say, what do we want to accomplish? What's the science we want to do? We call that a decadal survey. Okay, so Hubble's mission was to see farther in the universe than we could ever see before, solve the problem of the Hubble constant, which they did for a little while. It's broken again. Okay, but we had a whole list of scientific objectives that we wanted it to accomplish. Okay, and one of the things we wanted it to do is take a picture that we call a deep field. Okay, so this is the winter sky, which we are rapidly approaching. This will be our nights now for a few months. Okay, so there's Orion over there on the left. You can see the 3 belt stars and the sword of Orion hanging down from it. And unless you're a constellation nerd, you don't always notice the constellation winding away from Orion's knee, which is Eridanus, the great sky river. Okay, and if you look along Eridanus in all the bows of the river, there will be places where you see big black spots, some places where you see a few other stars. But over here between Fornax and Eridanus, there's a particular place in the sky. And when you look, if you have good skies and good eyes, right? Mag 6 skies here in Nashville, is that what we have? Okay, maybe not. Okay, but Jay, but if you look in that corner of Eridanus, there is a spot in the sky where there is not anything that you and I could see with our naked eye or with any telescope you and I have access to. As far as we were concerned, we thought it was a blank spot in the sky. So for 10 years, we had Hubble go back and look at that spot and expose over and over and over and over again until it had a 26-day-long exposure. How many astrophotographers in the group? Okay, have you done a 26-day exposure?
Oh, sure, all the time.
Okay, I'll Steve's done it and Hubble's done it. Right, okay? So, and the outcome of that is what I regard to be one of the most remarkable and revelatory images that humans have ever taken. Okay, and some of you will be familiar with it. Does anyone know how big Hubble's field of view is? Okay, so if you take a dime and you hold it up at arm's length, Hubble's field of view is the size of the eye on Roosevelt, held at arm's length. Okay, so the picture I'm about to show you is the size of Roosevelt's eye held out on a dime out at arm's length. Okay, okay, and NASA doesn't use telluride circles, but I do. So. Okay, okay, so this is the picture. This is called the Hubble Extreme Deep Field. They took this one because they took the deep field and they're like, holy frap, what did we just see? And so they went and took an even deeper one, which is this one. And then there's an even deeper one called the Hubble Ultra Deep Field. Okay, but this is the Hubble Extreme Deep Field. There is a star in the field there, okay? But every other fleck of light that you see, every little smudge of color, every little whatever it is another galaxy. And we had no idea. We knew there were lots of galaxies, right? You go look at Virgo, you're like, man, there's a ton of galaxies, right? But this, in the size of Roosevelt's eye, there are some 5,000 galaxies in this image. Now, why did we do that? Because what we want to know is what's out there in the universe. In all these places that you and I as humans will never, ever get to. And we can figure that out. We can take the number of galaxies that we see in this spot. We can say quite reasonably that this spot is not special compared to any other spot in the sky. And we can multiply up by the number of Roosevelt eyes it will take to cover the whole sky. And if you do that, you will get that there are some 500 billion galaxies in the entire universe. Okay? Now, those of us who grew up with Carl Sagan, we're used to big numbers like 500 billion, billions and billions, right? That's what it was. Okay, but that doesn't really capture what that number really is. Okay, so has anyone here who's, well, maybe when you were 10, has anyone tried to count to 1 billion? Okay, if you say one number a second, how long is it going to take you to count to 1 billion? Over 30 years. 1 billion seconds, smarty pants over here. It will take 31 years, 31.6 years. Okay, 31.6. Okay, that does not capture how enormously large a number like 500 billion is. Okay, so we're astronomers and we all learned from Carl. And so many of you probably know Kelly Holly Bockelman at Vanderbilt. So Kelly's a colleague of mine. And so I like her word, right? So her word that we like to use for this is, it's ginormous, right? That's the only thing we can do. It's so big, we have to make up a word that captures how mind-bogglingly large the universe is. Okay? Now that was Hubble. That was 30 years ago. Okay? Today, we use this telescope. And in the first image that they took with JWST, we get the same kind of nonsense that we got from Hubble with a 26-day exposure. Okay? So we're going to take deep fields with JWST. And that number, I predict, I'll bet you a Dr. Pepper and a bag of jelly donuts, that number for the number of galaxies is going to go up. Because the farther back we look and the harder we look, we see more all the time. Okay? Now, 500 billion is not really such a huge number. There are bigger numbers in the cosmos. So, I used to live on the shores of Lake Michigan, and quite surprisingly, if we go down to the shores, you can find beaches, sands, okay? And you might very innocently ask, how many grains of sand are there on Earth? Well, you can figure that out. You can figure it out the same way we figured out how many galaxies there are. You can take a handful of sand, you can count the grains as they fall out of your hand, and then multiply up to get how much sand there is in all the beaches and all the deserts. Okay, would someone like to hazard a guess as to how many grains of sand there are on Earth? Billions and billions, right? So there are 10 billion grains of sand on planet Earth by doing the experiment I just told you. Okay, so it took 31.6 years to count to a billion. You have to do that 10 billion times to count to the number of grains of sand there are on the Earth. No human, as far as I know, has counted to a billion. No human can count to 10 billion. That is a number so large that you and I physically cannot count to it. But we have the ability to figure out that that's the right answer. Okay? Now, there are still bigger numbers, right? Because when you and I are standing out looking at the Milky Way, we can ask, how many stars are there in the galaxy, in the universe, whatever you want, okay? And so
You could go back the other way to how many atoms there are in a liter.
we'll get there. We'll come back to that right at the end, right? Yeah, this is where we're going, right? So if I were to count all the stars in all those galaxies that Hubble said, right? I do the thing that we've been talking about doing. I count all the stars in some unit I can count, and then I multiply up by all the ones that exist. So I have to figure out how many stars there are in the Milky Way. And then I will assume, reasonably, it's not perfect, but it's close enough, that every galaxy is like the Milky Way. If I multiply those 500 billion galaxies by the number of stars in the Milky Way, I get the total number of stars in the universe. Okay, that number is pretty big. Right? If I do that, there are 100,000 billion stars in all the universe. Now, when I do my talk about life in the universe, I use this number too, but that's for some other day.
Only one.
Okay, that's 10 sextillion stars. Okay, this is beyond any number than we have ever encountered or will ever encounter on Earth. There's this famous thing that I think it was Feynman who said, right, we shouldn't call these numbers astronomically large. We should call them economically large when you're talking about numbers like billions and trillions, right? But these numbers, there is no human context for a number this large. The only thing we know that's this large is when we're talking about the universe in mass. Okay? And it melts your brain. And you get to a point where you're like, oh yeah, 10 sextillion stars, right? We're immune to how large it is. Okay? But if you think about it for a while, then you ask yourself, when everything is so impossibly far away, and when these numbers are so impossibly large, when there are so many things in the cosmos, how can I figure anything out at all? And the answer, of course, is we do, because we have libraries full of science books that have captured all of the knowledge that we as humans have accumulated. Okay, this one right here is called the Astronomical Journal. This is one of our main journals in astronomy. It goes all the way back to the 1800s. Okay, and it's not the only astronomy journal there is, but we summarize all of the things that we've learned. And when the universe is as big as you and I are talking, how do we discover anything to write down and pass on to our fellow humans? And the answer is, we have a powerful tool, and it's called asking questions. And it's what we as scientists do every single day. And my message for everyone always is it's what all of you do every day as well. Okay, now amateur astronomers are an easier lot to talk to because you're already invested in being scientific and thinking about science. But the vast majority of public crowds I talk to, right, they remember having bad experiences with science, right? If I sit down on an airplane and I tell someone I'm a physicist, right, they make a face like they've eaten a bug. And they're like, I'm gonna go talk to this dentist about root canals, right? Because they hated physics, right? But the truth is, all of you practice science every day. And it's because you know how to do what we as scientists do. You ask questions, you look at what's going on to answer that question, and then you go on to the next question, right? When you walk into a room and you flip the light switch and the lights don't come on, what do? Oh, no light for us. No. You begin doing what scientists do. Why didn't the light come on? Is the light bulb burned out? Well, this light works, so it must be burned out. Is it screwed in all the way? You go screw it in. Yep, it's all screwed in. Is the cord good? No. And then eventually you replace the light bulb. You do science in your life every day. You just don't know you do science. Okay? So Carl Sagan, I'm a Sagan nerd, right? So Sagan once likened this whole game of how we do science to playing 20 questions. Okay, does everyone remember playing 20 questions? Right? 20 questions, all you can do is ask questions that have a yes, no answer. Okay? There is something underneath that circle. Go.
Is it yellow?
Is it yellow? No. A little bit. We've already violated it, okay? Okay, question 2.
Is it a planet?
No.
Is it a food?
No. Okay. We just asked 3. We'll not go through all the 20. But let's just think about those 3 questions. Okay? With 3 questions, you've already eliminated vast amounts of the universe. Right? You asked, is it yellow? Well, that means it's not those books aren't yellow. It's not that wall. It's not the observatory dome, right? It's not all the trees. Well, some of the trees are yellow, I guess. Right? Okay, right? So you can eliminate things that are yellow. What was the second one? Which is a planet, right? Okay, how many planets are in the current planet catalog? Anyone know? I look every day.
6,000.
7,000. Okay, so there are 7,000 planets strewn across. You know it's not any of those. Okay, is it food? It's not pizza. It's not submarine sandwich. It's not lasagna. It's not gummy bears. Right? Every food you mix. It's not right. So if you took 20 carefully chose questions, almost always you're going to figure out what's under there, and you would discover that it's a few people asking questions about the cosmos. Okay, so that's Lego me. Okay, that's Lego Neil deGrasse Tyson. I keep tweeting this question. I'm going to ignore it. Okay, so you can do this with literally anything. And as astronomers, it's literally the only thing we can do because no human has been farther from Earth than the moon. Everything we know about quasars, black holes, planets, stars, nebulas, other galaxies, dark matter, and dark energy is because we have stood here on Earth, used an instrument like that one, and looked out into the universe, and all we can do is ask questions and figure out what the answer is based on what we can see through our telescope. That's the power that asking the right questions has, and it's what we do as astronomers every single day. And in reality, it's what every one of you does every single day as well. Okay? So, we call this game, as we say, science, right? This is literally what science is. Asking questions, finding answers. That's all it is. Okay? It requires you to have a fastidious belief that data tells you something. You have to look at the world around you and you have to accept what you can see. If you don't understand what you see, you have to make new observations. That's why we built Hubble. We didn't know what the Hubble constant was. We thought we knew what the Hubble constant is, and now we don't know what it is again. Because we keep looking and we ask new questions and we're like, oh, okay, well, maybe not quite what we thought. Okay, that's the way this works. Science is a self-correcting and evolving process. And one of the things we struggle a lot with is that people get indoctrinated into the idea that science gets written down in a book and it's static. If I go look it up on Wikipedia today, that's what it'll say on Wikipedia 5 months from now. But no, right? If we discover something new, we got to update it. That's the way science works. That's the way human knowledge evolves. Okay? Okay. So, you and I live in an age where information is at our fingertips. That's kind of how we started off. We all know what the blue marble is, and we've all seen the blue marble picture, okay? And so it's really hard to believe what the world was like before we had that kind of civilization spanning common knowledge. the stuff that you and I get through our common education. But I think it's productive and I think it's useful to think about what the world was like before we knew all the things that you and I kind of take for granted. It helps us actually look at the things we're discovering about the cosmos through new eyes so that we can think carefully about why we think certain things mean certain things and what kinds of new questions we can or should ask by revisiting the way we discover things and the way we used to think about the world. It helps us keep our brains fresh and flexible as we encounter new ideas. Okay, so when you and I stand outside, right, we can see the sky. There are basically three things you can see. You can see things in our solar system, sun, moon, and planets. You can see stars. And in a few instances, you can see things that are farther away, like the Andromeda. Not very many. It's mostly the planets and it's mostly the stars. Okay, and so for a long, long time, all we knew was those things. Okay, and there was a time not that long ago where we didn't even know what those things were. Before the invention of the telescope, just 400 years ago, we knew the planets were there, but we didn't know what they were. We just knew they were bright lights in the sky, just like the stars, that moved in funny ways. We speculated about what they were, but we didn't know what they were. Okay? So let's pick a couple of those things. So Galileo's the one who changed all this. So tell me what you know about the moon. Let's just start with the moon because it's easy. What do you know about the moon?
Earth's only natural satellite.
It's the Earth's only natural satellite.
Slowly moving away.
It's slowly moving away. That's true.
It's gravitationally locked.
It's tidally locked, as we say. Yes, that's right. Yeah.
It has craters.
It has craters.
It has weak gravity.
It has weaker gravity than Earth. Okay. Okay, we could go on like this all night. Okay. How many of you have laid rulers end to end and measured the distance to the moon? Oh, yeah, right. You're laughing. I've shined a laser pointer at the moon. It hasn't come back. Okay. Okay. How many of you have seen the craters on the moon? Through a telescope. How many of you have visited the craters on the moon? I get other answers, right? We get there are mountains on the moon. We get there are dust on the moon, right? Okay. But that's all the common knowledge of our civilization. Okay. Before we went to the moon in the space age, this is what we knew. Okay, so this is a model of the moon at the Adler Planetarium in Chicago. It's about 5 feet in diameter. Okay, it was made by Rand McNally in the 1940s. No satellite had ever been to the moon. We had telescopes. There were amateur astronomers in the 40s. Were any of you amateur astronomers in the 40s? Anyone by then? No? Okay. Okay. So no amateur astronomers that old here. Okay. But this was it. They only made half the moon. How come? We've never seen the other side. Okay, Adler also has in their collection globes. There's probably some back here. And if you look at them, they're printed on one side and the other side's blank. Because they have never seen the far side of the moon. Okay, so this looks like you and I imagine the moon because we're amateur astronomers. We've looked at the moon through our telescope all the time. This is what it looks like. But what would I have to do with this 5 foot tall model? How far away would I have to stand from it for it to look like the moon looks to me to my naked eye?
1,000 miles.
1,000 miles? Any other guesses?
500 yards.
500 yards? So two extremes there, 500 yards to 1,000 miles, and the other. Okay, so about 140 meters. Okay, so about a little bit less than half of your distance, quite a bit less than the 1,000 miles. Okay, okay, but that's about the length of a football field, including the end zones. Okay, so if you took this and you put it 140 meters away, what would you be able to see? What can you see with your naked eye?
Just the seas. The Moray.
You see dark spots, the Maria, and you see the terrae, the height spots, but there's no craters you can see. There's no mountains you can see. There's no canyons. None of the things that all of us know are on the moon can you see, right? The moon looks like an irregularly colored orb. How big is it?
2,000 miles.
Nope, in the sky. Yeah, half a degree. Okay, but you all know that half a degree is about the size of the dime that you were using to do the Hubble Deep Field. Okay, so the lesson here is the dime is your most valuable astronomy outreach tool. Okay, so it's about the size of a dime. Okay, I learned that by doing the Astronomical League's lunar, right, doing the moon illusion thing with it. So, okay, so it's about the size of a dime. Okay, here are Galileo's first sketches, which many of you may have seen, right? Galileo pointed his telescope at the moon and he saw what you and I see. He saw the craters. The first person in human history to know the moon wasn't smooth. And he was astonished and he didn't believe it. He had built a brand new scientific instrument that no one had used for this purpose before, and it had shown him something that no human had even speculated at. And so he had to convince himself that it was true. That's my email that keeps blinking. I should shut it. Sorry. So he took an Italian coin and he stuck it in the wall on the far side of his courtyard. And he looked at it and sketched it through his telescope, just like he was doing for the moon. And then he went up and looked at it from 2 inches away to convince himself that the telescope wasn't lying to himself. Okay? And so this is what he wrote. He said, the moon certainly does not possess a smooth and polished surface, the conventional wisdom. He said, it's one that's rough and uneven, and just like the face of the earth itself, is everywhere full of vast protuberances, deep chasms, and sinuosities. Okay, and you see Galileo doing what we as astronomers do every day. He's applying the Copernican hypothesis. There's nothing special about Earth. So if I see something happening elsewhere in the universe, it's probably the same kind of thing happening here on as we see here on Earth. So if we have chasms on Earth and it looks like a chasm on the moon, it's probably a chasm on the moon. Okay, so you see him doing that facetiously. So that's in Sidereus Nuncius. Okay, and Sidereus Nuncius was the book he published in 1610 about all the things he saw through his telescope that literally transformed the universe. Okay, so this is a conjunction from about 6 years ago. Okay, so this is Jupiter and Saturn, I think. Yeah, I think it was Saturn. Okay, you all know how big this is in the sky? Okay, so it's about the size of your dime there. Okay. Your dime is your most valuable astronomical friend here. Okay, so Galileo looked at the planets too. Okay, and what Galileo discovered when he looked at the planets was that the Earth is a planet. The first planet discovered was Earth. Not because we didn't know it was here, but because we didn't know it was the same as all of those other things in the sky. Okay, now it's not the same. It is the same from the Copernican viewpoint, right? They all go around the sun. But the fact that they were worlds is what he discovered, that the Earth is just one of many. Okay? If you go read about scientific history or mythology or religious history before Galileo, the Earth is the firmament. It's the foundation of the universe. And what Galileo discovered was that the Earth is a planet. That's how dramatically the worldview changed. Okay, and so the pictures that he drew, these are famous ones. He saw Venus go through phases. That's evidence that Venus is closer to the sun than we are. He drew Saturn. So his famous picture of Saturn up there, he didn't realize what the ring was. Does anyone know what he said about Saturn?
Ears.
Saturn has ears, right? So it wasn't until Christian Huygens built his refractor that we were able to discern it was a ring. Jupiter, through Galileo's telescope, was featureless, although he did discover the moons orbiting around Jupiter. So he discovered that the moon is a satellite, just like Jupiter has satellites. Okay, and then his sketch of Mars was just a circle as well. Okay, so he discovered that the planets are not stars, but what he discovered was that the Earth is one of the planets. Okay, so that's the kind of power that asking these questions have. So tell me what you know about Jupiter. It's the biggest planet in our solar system. Okay, good. The big red spot. Yes, we'll talk about the big red spot.
The big red spot has shrunk.
The big red spot is changing, yeah.
It's changing.
When I started in amateur astronomy, my friend who was teaching me amateur astronomy, he called it, he's like, yeah, we can see this. We call it the sort of okay red spot. Because it's been tricky. Anything else? What else do you know about Jupiter?
Metallic hydrogen.
Yeah, the core is probably metallic hydrogen. We haven't tested that yet, but we think that. That's right. Okay. So there's a lot about Jupiter that you know. But how many of you have been to Jupiter? Oh, right. Okay. That time I was reading Carl Sagan, right? That's when Voyager was going to Jupiter, right? And I can remember because we didn't have the internet in those days. You all remember the days when we didn't have internet?
What?
Right? Right. I know. Can you believe that? Okay, so in order to find out what Voyager was discovering about Jupiter, I had to wait for that National Geographic to come, right? With those pictures that Voyager was sending back. Okay, and what will freak you out is go dig out your National Geographic if you have it and look at it. Okay, but then go look at the pictures on the NASA website because Voyager sent pictures back in like 640 by 480 format, right? They are tiny compared to the pictures that you and I are used to. But nonetheless, those kind of iconic pictures of Jupiter that we all have in our heads came from Voyager. Okay, so Voyager is kind of exemplary of the way that we are observing the nearby universe. You and I, as humans, can't get out to these places, at least not easily. Okay, contrary to our science fiction that we like to watch. Okay, so we build robot emissaries to do our work for us. And this is really a testament to our power to harness technology. You and I do this, right? We have telescopes that would have made, professional astronomers cry in the early, 19th century, right? But technology able to go sample the universe and do scientific measurements that tell us the things we would like to know is something that's relatively new. And it doesn't always work, and sometimes it works great. And in the case of Voyagers, it's been working absolutely outstanding. Currently, the two Voyagers are the most distant objects that humans have ever built from the Earth. And this month,
It's a solar day.
it'll be a light day away. Okay, the farthest anything's got from Earth. Okay, so that means it takes light one day to get from us to Voyager. Okay, so Voyager was truly one of the most remarkable spacecraft we built. But I have a favorite picture from Jupiter. Okay, does everyone have a favorite picture from Jupiter? Okay, everyone should have a favorite picture from Jupiter. Okay, so go look at all the Jupiter pictures and pick your favorite one. But this one's my favorite, right? And I can remember seeing this one when I was young. Okay, right. I would love to have this one blown up to 5 feet by 5 feet on my living room wall. Because if you weren't an astronomer, if you weren't one of us, you would look at this and think it's an abstract painting. And it is an abstract painting, right? It's nature painting with clouds and elements and chemicals. Okay? But this is what the universe does. We learn all the things you and I are trying to learn. We develop awesome technologies by building the spacecraft. We learn the size and scale of the universe, right? We learn why aurora happen and why hurricanes happen, right? But the other cargo that this exploration gives us is things that you and I would regard as art that yes, the picture right here. What is this? This is in an old Scientific American, right? There's the picture we're talking about, right? You knew it was in there. Okay, right here in the front row. Okay, so right. This is why I was telling you I love about Sagan, right? Sagan was never afraid to embrace that idea that as humans we're moved emotionally by all of that, and this is what that picture does for me, right? When I think about the size and scale of the universe, the things that move me, the things that change me, the things that make me really sit and think hard are the things that kind of, drag my brain in weird emotional directions. And sometimes that's something as striking as a piece of art, which in this case happens to be one of the most remarkable astrophotographs that Voyager returned from Jupiter. Okay, I love that. But most people, the most famous picture that Voyager took is this one, right? Y'all know what this one's called? This is called the Pale Blue Dot. Okay, there's a famous soliloquy that actually there's a recording of Sagan reading it, but it's from his book A Pale Blue Dot. But it's about the size of the Earth. Okay, and this picture is the picture which really pushed him down that way of thinking, and it's a picture that almost didn't get taken. Voyager had passed Neptune, and they were starting to power down all the instruments and just leave on the solar experiments. They were looking for the edge of the solar system. And Sagan convinced them to turn Voyager around and take what's called the family portrait. They took a series, I think it's 68 photographs across the plane of the solar system that captured all of what currently are the known planets in the solar system. We did not include Pluto. Okay, yeah, I know, I make that face too. So, okay, we'll do the Pluto talk sometime. I also did a TED talk about Pluto. That's another story. Okay, so he took this picture, and this is the frame that had Earth in it. Okay, the colored striations are a lens flare, and photographers will know this. It's a lens flare from the sun. Okay, because the sun's the Earth was very close to the sun in this image, and it's right there, that little pale blue dot hanging there. And there's no picture I think of Earth ever taken that shows how really kind of far away and alone we are compared to this one. And that inspired Sagan's famous soliloquy that is quoted so often. Okay, so there's a circle for people who didn't see it. But the real reason I talk about Voyager takes awesome pictures that kind of illustrate this thing. But there's something very important about Voyager that I think really reflects how we as humans actually think about our place in the cosmos. Okay, and that thing is the golden record. So this started with Pioneer. The Pioneer 10 and 11 both carried plaques, which famously caused a lot of consternation. Does anyone remember why the Pioneer plaques caused consternation? Yeah, they had engravings of nude humans on them, which disagreed with some folks. Okay, there are scientific reasons we did it, but that's another discussion. But when we sent Voyager, we also wanted to include something that represented the civilization that built it. Okay, and this was the point in the Pioneer plaque. These spacecraft are outbound out of the solar system, and they will outlive me and you and our civilization. They will sail into the galaxy for 1 billion years, and on the off chance that someone might stumble across them, we wanted there something to be on the spacecraft that said something about the civilization that sent them out. On Pioneer, it was just a plaque with some engravings, abstract engravings about where it came from and the people who sent it. But on Voyager, we sent actual data, okay, in the form of a phonograph record. Okay, so the record's down here on the bottom. Okay, on the top is the cover, and the cover has the instructions for how to read the record. Also included under the cover was a spare phonograph, so you could actually get the information to the record. Okay. Now you can go download the data from the Voyager record, and there are amateurs, for those of you who like Python projects in the evening, who have written their own Python codes to decode the Voyager data. Okay, it's doable. It's hard, but it's doable. Okay, but let me tell you what's on there. Okay, so there are greetings in 55 different languages. The most famous one you will hear here in the United States when you see documentaries is a young girl saying greetings from planet Earth. Okay, but there are 55 additional languages and greetings. There are 115 images of life on Earth. There are pictures of babies and humans in marketplaces and desert islands and animals and cities, right? 115 pictures designed to show you the breadth of what life on Earth is like, not just humans, but our ecosystem as well. There were massive debates about what those pictures should be. In particular, there was a conscious choice made by the scientists to not depict any images of violence or war. Okay? And people were like, well, that's what humans are all about. We should totally not, we're lying about ourselves, aren't we? And the scientists are like, maybe, but we want to be optimistic that we as humans will evolve past that kind of impulse that the reptilian depths of our brain like us to engage in violent conflict. So why put that on as one of our precious 150 images? So the choice was made not to do that. But the rest of it is about life on Earth. Okay? So there are 90 minutes of music. Earth's greatest hits. Okay? Bach is the only one who's on there twice. There is a Peruvian wedding song. There are chants from the Indonesian islands. The only rock and roll is Chuck Berry. There's a famous Saturday Night Live skit where aliens discover Voyager. Steve Martin plays the aliens, and the only message they have for Earth is send more Chuck Berry. So there's this 90 minutes of music. Okay, so there was a Kickstarter several years ago to press new vinyl versions of this record, so you can actually get all the music that's on the Voyager record. You can get it online as well, but it's so much cooler to play it in vinyl. Okay, so 90 minutes of music. Okay, and then lastly, there is a final message which almost prevented the record from being sent. Okay, so it's engraved in hand. It's written right, you can't see it in this projection, but right here around the inside edge, inside the tracks, is a handwritten message in English that says, to the makers of music, all worlds, all times. And the reason it almost kept the record from being sent was because NASA was going down the checklist, and some engineer said, this isn't on the record checklist. We should take it off. It's probably broken. And so they had to do some fast dancing, say, no, it's okay. We're going to send the record. And so the record's went. Okay. Okay. So you can get all this online, as I said. There's a great site at Voyager, jpl.nasa.gov. They'll also tell you where Voyager currently is. And Ozma Records are the folks who repressed it if you want to do it yourself. Okay. Whoops, I'm sorry, Tom. Okay. Everyone's taking pictures. I'll send my slides to Tom if you don't want them. So okay. So why is the Voyager record part of, oh, I'm sorry, question. Yes, I didn't see your hand.
I'm not sure I wanted to show it, but
You should feel completely confident.
is there a record player?
There are instructions for how to play the record and the phonograph needle you need. Right? We did not send the record player, right? Okay, but if you look at that cover, right? So, whoops. Okay, so this right up here, this right here, this shows you taking the phonograph needle and running it around one of the grooves on the record. This is a depiction of the record, and it shows you how the data is laid out around one of the records. And so then as you get the data out, this is what it will look like coming out of the needle. And then this is how you take it and you reconstruct it to make the images. And this is what the first image on the record looks like. Okay, so you'll know if you're getting it right. Okay, now the debate among astrobiologists, so if I ever give you the astrobiology talk, is, well, are aliens really going to understand that? Okay, but these amateurs, so apparently there are people who don't know the story of the Golden Record, which astonishes me, having grown up in the Golden Record era, right? The amateurs who tried to do it, they heard, oh, there's a record on Voyager. And so they purposefully then stopped trying to learn anything about it. They went and got the images, they got the raw data, and they did what an alien's supposed to do. They tried to decode the record and they succeeded, right? And this is kind of the ethos of all of these messages we send to the cosmos, right? Which is, we're going to send these as scientists, assuming that the people receiving them are scientists, or at least know about mathematics and science the way you and I do. Okay, so all of this is encoded numerically using multiples of the wavelength of hydrogen, which is the most common element in the universe, right? So that's how the number system is encoded. And so anyone who's capable of understanding technology will know that and be able to decode the number system, because numbers aren't unique to Earth, they're part of the language of nature, right? So this is the ethos. And so the amateurs figured it out, okay? And so you could be like, great, that means aliens can figure it out. Except, you're shaking your head, right? Amateurs are from your culture, right? Mm-hmm. They have been taught mathematics and science the way you've been taught mathematics and science, right? So maybe this picture is something that's easy for you and I to understand, because if I go put, a coffee cup down in front of a shark, he won't know what a coffee cup is. But if I put a coffee cup down in front of someone from Lithuania, they do. Even though they don't speak English and I don't speak Lithuanian, right? So there's these kind of questions about, does culture help you? So, these are the things we debate, okay? But this is actually at the heart of the point, right? Why do I tell you this story? Because I think it represents what we as humans have at our core, which is a very optimistic view about what our place in the cosmos is and what it would be like if we could communicate with other people in the cosmos. We know how small we are. And we know how big the universe is, as you and I have just discussed. Yet we have enough optimism to imagine that almost impossible odds that someone might one day stumble across the remains of our little robot emissary and decode a message in a bottle that it left on the side in the form of a golden ring. That's not someone who's kind of a shrinking violet and kind of depressed because we think we're so small and insignificant. That takes a lot of optimism about what the possibilities for the future might be. Okay. Now, does anyone else want another bet for a Dr. Pepper and a bag of jelly donuts? Okay, because I have the following bet I like to make would be this: who I think is going to find Voyager are our descendants. They're going to travel out into space. They're going to leapfrog over us. And 50,000 years from now, there's not going to be any memory that we sent Voyager. And they're going to stumble across this thing. And be like, what is this? And they'll decode it. Just like you and I find a shard of pottery in the Syrian desert from 5,000 years ago. We don't know who built it. We don't know who made it. We don't know who lost it. But it's evidence that they were there. And I'm willing to bet Dr. Pepper and a bag of jelly donuts. That's a pretty solid bet, right? That humans or our descendants are like the most likely ones to discover Voyager. And when they discover it, its mission will be accomplished as it was intended. Someone who knows nothing about us or our world will be the ones to discover. Yeah, right?
You'll be a gorilla.
Yeah, right. The whole Planet of the Apes thing is going on, right? So, okay, so here let's tie up.
Paradox ever come up in these discussions?
Yeah, we talk about Fermi's paradox a lot. Yeah. So Fermi's paradox is, for those of you who know, so Enrico Fermi was a nuclear physicist in Chicago. He worked on the Manhattan Project, and so he famously addressed the question of life in the universe by asking, if aliens exist, then where are they? Because if life is plentiful, someone should have already been to Earth because they're doing things like sending Voyagers all over the galaxy, okay? And they're not here. Okay, so this has vexed astrobiologists for a long time. What?
Are you sure?
Well, right. This has vexed astronomers for a long time. And so there's, I have a great book called 75 Solutions to the Fermi Paradox, right? And it's like all kinds of different ways we can imagine that the Fermi Paradox, it's okay. Okay, and one of them is, we're the first ones. That didn't really make sense, but maybe we're the first ones. Another one is, they know we're here and they're scared of us. Another one is, wouldn't you be, right? Yeah, maybe they're here, right? These are all resolutions to the Fermi Paradox. Okay? Now, to tell you how much astronomers think about, I have 2 editions of that book. And the first edition I have is called 50 Solutions to the Fermi Paradox. And in the intervening time for the second edition, they added 25 new. So we think about this a lot, and it's a big problem. Yeah. So, okay. Okay, let's.
Some and they missed.
Yeah, right. There's all kinds of stuff. Yeah. Well, we can talk about that too. So, okay. Okay, so let's go back to this. Okay. So there are 100,000 billion stars in the universe. Okay. But let's imagine a rainstorm where some rain has been splattered on your window. Okay. In just 10 drops of rain, there are more molecules of water than there are stars in the entire universe. Right? So there are even bigger numbers and bigger cosmic thinkings, even right here at home. Now, some of you may remember that you and I are made of 60 or 70% water. Okay? And so what that means is that in you, there's more molecules of water than there are stars in the entire universe. And every one of those molecules of water is made of 3 atoms, 2 of which are hydrogen, which is what the stars are made of. And the other is oxygen, which is one of the things that stars make when they burn their hydrogen. And when stars end their lives, just like you and I do, they live long, lustrous lives, but in the end they perish. They take everything that they were and they throw it out into the universe. And it becomes you. And it becomes me. And so even though we are so small. We are part of that much larger cosmos. This is what Carl said always. We are star stuff. We're a way for the cosmos to do what we as scientists do, to put itself together in a form that can ask questions about why it's here and where it's going and what's the deal with all those other atoms in the universe. You're the cosmos made manifest in a very real way. And so when people wonder why we're here, I find that answer very comforting. This is just the universe trying to figure itself out, like my students trying to figure out their physics homework. Okay, we're just doing the homework the universe gave us, which is to figure out where we all came from. Okay? Okay, so I always like to give you a few things to read. So I will leave you with a few things to read. This is a very old movie. Some of you may know about it. It's by Charles and Ray Ames, who are a husband and wife team who worked at IBM in the 1970s. And so this is I will get out of the way here. This is a movie that they made. You can find it on YouTube that starts with a picnic. It zooms out to the largest scales in the cosmos, and then it zooms in to the most microscopic scale. Okay, and it's called Powers of 10. And it's just up in scale and down in scale to show you the extent of the cosmos in both directions. Cosmos, of course, you can read it, and you can still get it on DVD and probably streaming. And so I still find it great to read. Science has changed, but there's still plenty here to know. This book is really a fantastic book, especially if you like the astrobiology thinking. So this is a book by Rachel Sussman. It's a coffee table book. It's called The Oldest Living Things on Earth. And so she goes and visits the oldest living things on Earth and takes pictures of them. So there's like Balearic seagrass that has been around for 40,000 years. And she goes to see the bristlecone pines that have been there for 6,000 years. My favorite is in central Utah. There's an aspen grove that's 80,000 years old called Pango. So I go there with my telescope and I observe all the time because it's cool, right? This tree has been here for 1,000,000 starry nights. And I'm sitting here observing, right? I love that. So it's a fantastic book. This is a folk artist who I like very much. His name's Peter Mulvey. And so he has an album called Letters from a Flying Machine. So when he flies on airplanes, he doesn't watch his phone or the screen. He writes letters, handwritten letters to his nieces and nephews. And so he recorded a whole bunch of those letters as tracks, as songs on this. And one of them is a song called Vlad the Astrophysicist. So Peter's a folk artist, but apparently he has a friend like me who's an astrophysicist. He's a real guy at University of Washington. His name's Vlad. And one night they were sitting behind a hotel in West Virginia, and Peter asked him, Vlad, is there life in the universe? And so this is Vlad's answer to him that Peter captured in the song. And it's one of the most lucid explanations and answers to the Fermi paradox that I have ever heard. Okay, you can find it on YouTube. And there was a Kickstarter. You can also get a book of it. I don't know if it's still in print, but you can probably find one where the whole explanation is written in book form. So, but definitely go watch it on YouTube. It's perfect. It's really great. Okay, and this is a tiny URL that'll send you to the 10-minute version of this talk. Okay. Okay, so I'll leave you with the Carl Sagan quote. I've talked a lot about Carl, but this is from the fourth episode of Cosmos. He said there's a part where he's talking about why people believe in astrology and stuff like that. And his basic argument is people are trying to feel connected to the cosmos. And he says the desire to be connected to the cosmos reflects a profound reality, which is we are connected. We just don't think about it. Okay, and not in trivial ways, but really in the deepest ways, which are some of the things you mentioned. Okay, so I always like to, take that as my closing point and go to sleep and not let my brain melt too much. So, okay, so I'll stop there and say thanks for your attention, and I'm happy to chat for as long as folks want to chat. So, yeah.
Questions?
More questions?
Good question.
Yes, sir.
In your career, have you noticed recently an uptick of people that are like flat earthers and skeptical people? And what do you do to combat that? Because I know several, and they know that
Yep.
I'm astronomy, and it's just hard to sometimes reason with them.
So I give a lot of public lectures. I do about 20 a year. So I've done 350, 360 at this point. And I will get these folks in the audience And so, you know, they often want to engage, which I assume is your problem. They want to talk to you about this. And the question is, how do you engage, right? And so the viewpoint that I always take with them, which is really for flat earthers in particular, the foundation of their whole kind of belief system, which is don't believe anything you hear from an expert, go prove it yourself. And of course, this is what you and I were just talking about. This is the point in science, which is you absolutely, if you don't believe it, go prove it for yourself. Okay. You have to do it. You have to produce data that everyone can agree on. And that's where most of them fall down. Okay. So I will commend to your attention a very great documentary called Behind the Curve. Maybe it's Beyond the Curve, but Behind the Curve. It's about an hour and a half where they follow these flat earth folks. Okay. And can I give spoilers? Is it okay? Does anyone care if I spoil it? Okay.
Oh, yeah.
Okay, so at the end, right at the end, they follow these flat earthers who are trying to do the experiments, and a group of them had rediscovered something called the Bedford Canal experiment. Okay, so the Bedford Canal experiment is you set up a row of markers of even height along the canal, and because the canal is supposed to be a level surface of water, if the Earth is flat, they should all stay at the same way. So you basically set up like a row of posts and you put holes in and you shine a laser and better go through all the holes. But of course the Earth is curved, and so the one gets low, and so it misses on the other side. So the ending of this documentary is these Bedford Canal experiment guys going, it's lower than we expected. What's going on? Which is like, you're so close to the truth, right? Okay, and so that's great because as long as they agree with the compact that you and I as scientists make, which is we're going to have an unswerving dedication to believing our data, and if we don't understand our data, do more experiments. As long as they agree with that, they will get to the point where they will have irrefutable evidence. Okay. Now, the part that will depress you about that documentary is they have some Boeing engineers who are flat earthers. Yeah, right? Okay. Okay, but they're Boeing engineers, so they have stuff at their disposal. So they're like, look, we're going to buy these laser gyroscopes. And if the Earth is flat, laser gyroscopes across the Earth should give the same answer. Because if the Earth weren't flat, they would give different answers because the Earth is spinning. But the Earth's not spinning, it's flat. So these laser gyroscopes will totally work. So they buy 3 of these $30,000 laser, they distribute it across the Earth, and they're like, oh man, we got chipped. These are not calibrated gyroscopes. I'm just like, okay, so there are impossible folks out there that you're never going to make progress with. So the tactic I take is I stick with what I believe, which is we can test any question you want to test. Okay, but our job is to take the data and interpret the data. If we don't like the data, we have to take more data. Okay, and the reason that's my tactic is because I know they're never going to get data.
Oh, thank you.
Yeah.
Are you familiar with James Burke's The Day the Universe Changed?
Yes, that is a
I love it.
fantastic.
Love
Yes.
it, love it.
Yeah.
But when you were talking about Galileo and how he revealed different
Mhm.
things, our universe changed.
Yeah, absolutely.
And
Right.
he goes through a whole lot of it.
Yeah, so James Burke is another, he was on PBS at the same time as Sagan. So The Day the Universe Changed is his modern one, right? Which is great. At the time Sagan was doing this, he was doing another one called Connections, which I also love. Yeah, so but The Day There Were Earth. So I do another talk about Hubble's discovery of the distance to the Andromeda Galaxy. Because that was, and Marcia Bartusiak, who some of you may know, she wrote a fantastic book about this because that was another monumental shift in astronomy as well. So yes, absolutely great recommendation. Yes, ma'am.
About other intelligent life out there. So
Uh-huh.
my bright son here really got into this mockumentary, Ancient Aliens.
Yeah.
And it just goes into like, yeah, this Egyptian pharaoh, he was
Yeah,
an alien.
Yeah.
And they were here before, and
Yeah.
they gave us all the technology in the 40s and 50s. What do you think of that? Is it? I mean, their job is to sell advertising and then excursions. So it's obviously it's a bit sensationalized.
So-
Is there any?
So this is the problem with the modern age, right? Is that when you and I were growing up, right? So I have a colleague. She was the chair of physics at Yale, but she and I had this discussion. When you and I were growing up, there were basically 3 ways to get information, 4 ways. It was ABC, it was NBC, it was CBS, and PBS,
And the library.
and the library. Okay, but the point is, they all had to say the same thing because there were only 4 ways, four sources for the information, right? And so the what do you want to call it? The ethics of delivering information to the world was different than it is today. Okay, today there are as many ways to get information as there are websites on the web. Okay, and there is no control, there is no authentication, and so the question is, what do we do about that? Okay, it's getting even worse with AI now because you can just make crap up, right? Okay, now the thing that we as a society have to do is figure out how to do what most of us learned to do a long time ago, which is process information and decide how much we should rely on. Okay, what is that truthiness of data? How do we decide that? Okay, and so part of that has traditionally been multiple sources, which of course you can't do anymore. And so more and more, and this is where a lot of the anti-science discussion is struggling, is we have to, as a society, value expertise, right? There's a reason I'm a physicist and I'm not a dentist, because I don't know crap about dentistry. I know a lot about black holes. But my dentist knows a lot about giving me root canals and not much about black holes. So I go to him for advice on root canals, and people come to me for advice on relativity. Right? That's what expertise is about. And with things like history and culture, we have experts who are about history and culture, and they apply to their discipline the same techniques and rigid professionalism that a dentist applies to dentistry and that a physicist applies to physics. They know how to grade their sources and trust their sources. They know how to ask questions and pose questions and decide what they believe and what they don't believe and why. And so for those of us who are amateur historians or amateur archaeologists, right, I think the thing that we have to learn is to trust them the way people trust me and you when they ask how far away is Jupiter.
It's harder for young people these days.
It's harder for young people.
Learned.
That's right. And that's why I say we as a society have to figure out how to teach it. Right. But I will say, right, when I was that age, you know, my favorite series of books was this guy, Charles Berlitz. Do you all know Charles Berlitz? He wrote this book called The Bermuda Triangle and this book called The Philadelphia Experiment. And it's about all of this kind of weird quantum mechanical stuff that's not even remotely true, right? But I ate it up when I was a kid, right? And the truth is, I mean, so I have this argument with people about bad science fiction movies. I love bad science fiction movies. Okay, right? The Core. Anyone seen The Core? Yeah, right. Okay, but that's because it keeps people engaged enough so that they can come ask me and say, "Hey, I saw this. Do we think it's true?" And it provides an opportunity for us to have the conversation about what scientists who really work in that field think about that and why. Right? So we have to, I think we shouldn't be afraid of it, particularly with young people. They've engaged. And so we should use that as a foundation to have conversations about how we process information. Right? So that's the tactic I would suggest is the good one.
There's a new science fiction movie that was done in Brentwood coming out at the Sundance Festival called Never.
Never.
Lil Callum is in the lead role in it. It's about
Rock and
time
roll.
travel.
Okay.
Time travel.
I'll add it to my list, right? Time travel movies are the best. Okay. Yes, sir.
When I was younger, and I think we came from the same generation.
Okay. Yep.
There was the theory that the universe was infinite.
Mhm.
Never ending. In fact, I think Einstein took that position at some point.
How is Fred Hoyle?
But
Yeah, Fred.
but
Yeah.
now we're like, well, the universe is 13 blank billion years old. But every time we take a deep field, we look out and we go, oh, well, we've seen all these stars out here and they're older than we thought they should have been.
Mm-hmm.
And then we take another deep field and same thing.
Mhm.
Is there a theoretical age limit for the universe?
Yeah.
Or could it just like we had it back when we were kids. It
Yeah.
is in fact
Yeah.
infinite.
Okay, so when I do, so I have a cosmology talk too, right? So we'll just set up
Or
the
no,
next
it's
10
your-
years of
yeah.
visits to BSAS, right? So in cosmology, we are very sloppy with the way we talk about the universe. Okay, and so I encourage us always to be careful about what we mean when we start talking about the universe being infinite. Okay, for the following reason. If I ask you what is the definition of universe you're using, what is it? When you say the universe, what do you mean?
All that is known.
Okay, all that is known. Does anyone else have a different definition they'd like to use? Everything. Okay, right? Okay, so I'm somewhere in between those two. So for the universe, I suggest that the operational definition that is most useful is the universe is everything that exists. Okay. Now, when we talk about what we as astronomers do, we are not talking about the universe. We are talking about the observable universe,
Right.
which is everything that we can see. Or to be more correct, it's everything which has had time to send us a signal traveling at the speed of light during the age of the universe. Okay, so the assumption is the universe absolutely can be infinite in size. It is not infinite in age. And those are two different statements. Okay. Right. Okay. So I'll let you go melt your brain on that. In 2 weeks, you'll send me an email at 2 in the morning. Okay.
Every time we say infinite, it just fill in.
That's
the
right.
blank.
Infinite
We don't-
is hard, right?
It's just another
But what
word
we
for
mean
don't
as
know.
infinite is we don't know where the boundary is, and we don't have any reason to expect there is a boundary. Right? Okay. Now, the age of the stars thing was the first big crisis in cosmology. Because before we had accurately measured the Hubble constant, we thought it was 80 or something. Right? That gave an age for the universe like 10 billion years. Okay. But you go look at the stars in globular clusters, and they're 13 billion years old. Okay, so that was the first cosmological crisis. That's what caused us to build the Hubble Space Telescope. So today, the universe age based on dark energy, dark matter, all that microwave background, that stuff, it's something like 14.7 billion years. And as far as I know, there are no objects in the universe whose age we measure by some other chronology gives us a number bigger than that.
Yet.
That's right. As scientists, we can't preclude that we're wrong and that we may discover something older than that. Okay. We do keep discovering more and more, but it's all at closer to us than the edge of the observable universe. So presumably it's all young. So, we'll see. Okay, right. That it melts your brain. Yes, sir.
So did the little red dots kind of throw a wrench in the?
Yeah,
works?
so the LRDs, as we call them, the little red dots, are these discoveries in the James Webb Space Telescope's deep fields, the deepest images they've taken so far. And they are, as near as we can tell, massive black holes at the boundary of where we thought galaxies and black holes began to form. The fundamental problem with them is we don't understand how to make big black holes that quickly in the universe.
They're like 300 million after Big Bang.
Yeah, they're really very soon after the Big Bang. And as big as they are, they're the kinds of things we think take billions of years. We would have thought took billions of years to accumulate. So this is the big mystery right now: is how did they form? We're confident they're there. Have I done the gravitational wave talk for you all?
That might have been the first one you
The
gave.
first
us,
one,
but it's
okay.
been a
So
while.
what I actually do in my day job is I work in gravitational waves. I work on a space mission called LISA. And LISA will observe black holes at that distance. And in particular, we will observe the growth of black holes at distance. So I think LISA will do something to help with that. But JWST is going to continue to put these on the table. And we will do a lot of work before then. So we may know more. But right now, all we know is they're there and they're bigger than we expect. I saw, yes.
So LISA is identifying those things that go beyond the visible portion of the electromagnetic spectrum.
So LISA is a gravitational wave observatory, or it will be being built. It will observe the universe using gravity, not light. Right?
Where's Lisa located?
Oh, sorry.
Where is it located?
It will be in space, trailing the Earth.
Oh, that's right.
Yeah.
Good.
So it's 2.5 million kilometers across.
Mhm.
So it's enormous. It's we shine lasers back and forth. And so it will be behind the Earth and follow the Earth around. So,
Line amplification stimulated by emission of radiation.
That's a laser, yes.
So if you just using lasers?
Okay, and the reason we use lasers, right? So this light that you and I are getting from all the light sources in here is what we call incoherent. That means it's coming at you with, so light's a wave, which you may have heard. It's also a particle, but for this purpose is a wave. So some of it's coming at you like this, some of it's coming at you like this, some of it's like this, and some of it's like this, right? It's coming at you in all kind of very random ways. What a laser does is it says, so we use atomic processes to make all light of a single color. So so the lasers we use are infrared, so it's perfect infrared light. And then all of the waves are lined up so that we can use the lasers to make very precise distance machines. Because it's all lined up together as it's traveling, right? Okay. I saw another hand back there in the back. Yeah.
Are there any planets in the universe that humans could live on? Like
Yeah.
planets that humans could live on?
So if you grow up watching science fiction, right? George Lucas and Gene Roddenberry told us there's lots of planets in the universe that you and I could live on, right?
Oxygen.
Yeah, all of that, class M planets, right? So the goal for astronomers has been to find planets that are, as we say, habitable. And what we mean by that is planets that are the same size and same temperature as Earth. Okay, now the ways that we have for discovering planets are very biased, as we say. They're very good at finding planets bigger than Earth. So we found lots of planets that are the size of Jupiter and bigger. We found lots of planets that we call super Earths, which are like 10 times the size of Earth, 8 times the size of Earth. Okay, but we haven't quite found one where we're like, that one's the size of Earth in the right place. Okay, so we're getting closer. Our technology is getting better. We're getting some that are very close, but we think there should be lots. Okay, to date, we've discovered. So I'm giving a talk tomorrow night in Evansville. For that talk, I'm talking to them about planets. And so I looked the number up yesterday, and yesterday the number was like 7,048 known planets. And in those, there are none of them that are exactly the way of Earth. Okay. But we've only discovered planets now for 10, 15 years, right? So by the time you're my age, there will be tens of thousands of planets, and we will be in that regime where our technology is good enough to get them like Earth. And we will know the answer to that question by the time you're in graduate school in physics.
When I was his age, there were none outside.
That's right. That's right. Yeah.
Zero.
There were zero.
They
When I
thought
too,
it was-
when I got my degree in astronomy in physics, there were no known planets except the ones in the solar system. Yeah. Okay.
And they surmised that there was one, and I forgot, in one of the Iridani constellation stars had maybe a planet.
Yeah.
That was it.
So the year I got my bachelor's degree, they had just taken the first image of Beta Pictoris, which is in Pictor, but it had a disk around it.
Mhm.
Right, so the disk that plants, and so that was right at the beginning of when we thought we were going to be able to detect planets. And then the first planets were actually discovered around a pulsar. Okay, so a pulsar is a dead star. Okay, so Alex Wolskin at Penn State discovered these in 1998 or 97, somewhere in there. And of course, those aren't planets like you and I live on. And so what we think happened is when the star supernova, it destroyed the planets, but it didn't spread them out enough, and so then they recollapsed. So if we went and visited them, they're not going to be planets like you and I would have thought they are.
They're
They're
gonna
like
be crusty things.
yeah, crusty, dead, jumbled up worlds, right? Yeah. But those were the first ones, and so it wasn't until the first actual planet that you and I will just recognize as a planet was discovered around 51 Pegasi.
Oh, yeah.
Okay, so that planet, we called it Bellerophon for a long time as a new name, an IAU name, which I can't remember. But it was one of these super Jupiters. But it was around the sun-like star. So 51 Pegasi is a naked eye star. You can, well, with good enough skies, so you can see it. And it's a solar-like star. So we were excited. But this Jupiter Bellerophon has a 5-day period. So we don't know how to make Jupiters that have 5-day orbital periods. So there are still mysteries.
It's close enough to be screaming in it.
That's right. Yeah, it's they call them roasters. Roasters is what they call them.
At least it exists.
Yeah, it exists. That's right.
Darn.
And now there are 7,000 others that we've discovered. And some lots of them are in orbits like Earth has, but none of them are quite like Earth. So that's a good question. Okay. One more and then we'll kind of let everyone go and I'll talk to anyone who wants to keep chatting. So
So I'm thinking about Lisa again, and I think about Arecibo in Puerto Rico, and Arecibo got destroyed, ruined or something like that.
hurricane destroyed it.
There are other places like Arecibo. How does Lisa, the information that was being received at Arecibo, there are other places like that around the world, and how does Lisa correlate that information with the information of those in places
Yeah.
in the world, which deals
So,
with.
so gravitational wave astronomy is brand new science. It's
Mhm.
been around. The first gravitational wave detectors that we use today were built about 20 years ago. We just celebrated the 10-year anniversary of the first discovery of gravitation waves. Okay, so 2015 was the first time we'd ever discovered gravitation waves.
And Einstein said they would be too weak to ever.
And Einstein didn't think we'd ever be able to detect them, right? He died not thinking we would be able to detect them. Okay, but you and I live in the future and we can. So in 10 years, we have discovered 400 gravitational wave sources with LIGO, this instrument that we built on the ground. We have colleagues who use telescopes like Arecibo to detect gravitational waves from massive black holes in the centers of galaxies. Okay, and just last year they made their first announcement that they can hear the background hum of gravitational waves from black holes across the universe. They use telescopes like Arecibo to do that. Okay, so it's kind of like before the meeting started and everyone was talking, you could hear everyone talking, but you couldn't understand what everyone was saying because everyone was talking. That's what they've detected. That's what we mean by hum. Okay. And then LISA will launch in about 10 years. Okay, because we have to build 6 copies of our spacecraft, right? So when we launch, we will also detect big black holes, but we'll detect tiny stars in the Milky Way. We'll detect things falling into black holes at the center of galaxies. There's a whole host of new things that we'll discover. And so earlier you said electromagnetic spectrum, and the point in all of these methods is there's a gravitational wave spectrum. Low frequencies are discovered with these folks who use Arecibo and radio telescopes. Middle frequencies are what we'll do with LISA. High frequencies is what LIGO does, right? So there's a gravitational wave spectrum, just like there's an electromagnetic spectrum. And each part of the spectrum is useful for doing different kinds of astronomy, right? So, okay, so you're living in the era where gravitational astronomy is becoming part of our astronomical toolbox, right? Okay. Okay.
Sort of related to that, I've often wondered why we have so much gold in the earth.
Yeah.
It doesn't seem to be that many neutron stars if they are the source of
Yeah.
what has been discovered about the is neutron star accepted as the source of
Yeah.
heavy metal?
So one of our great gravitational wave discoveries was in 2017. So we detected the collision of 2 neutron stars, which we could also see in gamma rays as a gamma ray burst. Okay, so that's the first time that ever happened. And so that paper is the largest paper ever written in astronomy. There were 4,000 authors on that paper. Okay, I'm on that paper. Okay, so right. And the importance of that discovery is before we detected the collision of the neutron stars, we could say all these things on the periodic table come from stars dying, but we didn't see enough supernovas to account for all.
You can't get tantalum out of a supernova, can you?
Well, right, this is the point, right? Is you can't get all the stuff and in the abundances we see. But if you add the neutron stars in, you can. Okay, and so lots of the heavy elements like gold and platinum, tungsten, whatever you want, right? The abundances we can see from the neutron star event, together with what we see from supernovas, fills out our expectations for what the universe is made of. And the amount of gold on Earth is not large, because when I compare it to the amount of silicon on Earth, it's not very much gold, right? So we know what we think the abundance should be, right? Just like what you and I were talking about, right?
Out of a star.
Well, no, but in a star I can measure it, right? Because I can measure the strength of the light I see from gold compared to the strength of the light I see from tantalum, compared to the strength of the light I see from chromium, right? I can measure the abundances from the spectrum of the supernova, or in our case, the kilonova. That's
Yeah,
associated
you
with
get
memory.
the atomic spectra.
That's right.
Mhm.
That tells me the abundances. Okay,
But
and so
that-
then the question is, what am I comparing that to? I'm comparing it to abundances here on Earth. And I get the abundances here on Earth the way you and I were just talking about.
Mhm.
I go dig up a bucket of dirt and I count how much gold and how much tantalum and how much aluminum, right? And then I multiply by the mass of the Earth, and that's how much gold there is on Earth. Right?
Well, that, you could do that, yes.
Well, that's the way we do it.
But you might have trouble finding all the sources.
Well, right. There are assumptions you have to make, right? And we make the assumptions that we always make, which is we do this in 100 places, and we say there's nothing special about these 100 places, so they shouldn't be any different than the other 2,000 places on Earth we could have done.
I guess I was more leaning towards the distribution coming from a neutron, a collision, neutron star
Mhm.
collision.
Mhm.
Does it, is there enough neutron stars to explain the observances we find here, or does that mean we're in an area of more
No,
neutron
No,
stars?
that's the right question to ask. And as astronomers, we think the answer is yes. Because we know how long we've been looking for them, we know how many we've seen,
Mhm.
and so we can multiply by how often they should happen, which tells us how much they should make.
That's the question. I
Right?
have
That's
to ask.
right. And so that's not a perfect measurement. There's an error bar on it.
Mhm.
But even though the error bars exist, within the error bars, it still gives us what we think is the right answer.
Thank you.
Okay.
Well, cool. Well, thank you, Shane.
Yeah.
You're great.
Thanks, everybody.
Oh, I love heavy metal. Let's take a little break. Get up, stretch your legs. I'm gonna use the restroom real quick and then set up my laptop. We'll do like a real quick abridged version for the board meeting tonight to work through some things, just our official business, and then we'll get out of here. But let's take a 5 real quick. Thanks so much.
No problem.
Yeah, it looks like you'll come back probably.
Yeah, there's always more to talk about.
Very interesting.
Yeah. No problem. Yeah. Hey, thank you for coming.
Very much enjoyed
Yeah,
your
yeah.
talk.
Thank you so much.
How was your trip down here?
It wasn't bad. I flew. So,
Okay,
yeah,
good.
I could have driven, but in
I'll
the,
get you like this. Okay.
Trust me. What do I have to do? I'm not doing.
Press the big white button.
You want me this
Uh-huh.
way or this way?
yeah, I was on that paper. Yeah. Okay, so that paper, so you can probably find it. The gravitational wave event was called GW 170817. So if you go Google that, you can probably find the
I'll
paper.
get another one.
Okay?
Yeah.
Yeah, well, that's what we do as authors, right? We participate in the science and they put us on the paper, right? It's like writing a report for school, right? It's what we do. So here, let me take this picture. We'll talk some more. Whoops, I'm sorry. Okay. Are you good?
What's his
name? Jane Larson.
All right, try another one when you say cheese deliberately. Check these out.
Yeah,
Great.
yeah, I'm glad you enjoyed it.
Enjoyed your part.
Glad you enjoyed it.
great.
Oh, yeah, okay, okay.
That's class plan.
Yeah, right, yeah, I know.
This guy knows.
I'm wrapping on you in the board, my word. Yeah, perfect, very sure. Yeah, Council Shields, I see those. Anyways.
Thank you again.
Yeah, no problem. Thanks for coming. Yeah. Okay, take care.
That everything that we see on the universe, like we're inside a black hole. Is that possible?
So I thought about it a little bit, right? There's a very famous physicist. He thought about this for a long time. And so the idea, so
Oh, that's okay.
So-
I'll hook you up on the net.
So if you mathematically write down what gravity predicts about black holes, several people put it on black holes. there are some black holes where if you go in one side, there's like a tunnel and you come out the other.
We have our.
And the other side is what we call a white hole.
Monthly at the event.
Okay, so John's idea was that maybe the beginning of the universe, what we currently call the Big Bang, is just like the output of a white hole, right? Which means we are on the opposite end of a tunnel from a
Oh, yeah,
black
yeah,
hole.
we.
So we don't know if that's true or not, but mathematically we can kind of think about it. We know we can't be inside of just any random black hole because we know things about the insides of black holes that we don't see around. In particular, there's this point called the singularity that like destroys you if you go near it, right? And we look around the universe and we don't see any singularities, right? So it's not, if we are inside a black hole, as you say, it's not like, but we are inside this boundary that goes talking to the we call the cosmic field. And it all started with something as well, whether it's thinking about a corporation. So a lot of people think about these when we often still learn about it. And so when I study, right, general relativity, what underlies this.
Didn't want to take any risks.
We worry about questions like the one you asked, then general relativity, and then they go say, they say.
Yeah.
Because. Okay, okay.
Yes, it does. We teased him that way. They made that
About stuff that you think's interesting.
Yeah, definitely. You know, I often, so I teach a lot of non-majors.
I'm still on Zoom here, so I'm gonna log out because you'll log on. Okay.
Yeah, I'm on. I teach a
Well, I have my husband, Joseph.
Yeah.
He passed away. And so I had, like, there was one student as a teen but I'm gradually getting homes for them. And we're gonna have a lot of rest, like, with whatever's left, but right now.
Right.
So maybe like, once the boards are here.
Oh, no, I'm good. It's funny because in the so I always go to Nice Guy Network and full of like some of the cool things and stuff to bring people like, oh hey, there's stuff going on, and they're celebrating the 10 years of yeah.
I'm supposed to NSN talk next week.
Oh, are you?
Yeah, but with the government shutdown.
Oh, yeah, they're shutting everything
They're
down.
not gonna be able to install probably with the rare stuff.
Yeah.
Logistic companies.
What are you talking about like Christmas and like
About 4 years. Yeah. Okay. Is this recent one? Oh, it's April. Okay. Okay, a few months old. Okay, yeah. That's weird.
He's been in
Yeah. So I go to strong class. I go lots of clubs like this. I visit like I have a couple clubs in Oregon.
yeah.
And then
Are we thinking about like a silent?
here's a house in Oregon. I've been to West Virginia, which is where Tom. Library, they can cross to library, helping clubs,
Yeah.
clubs.
Well, let me work on logistics and bring it in here and let people know. And then
Oh, here, okay. From where? Oh, from.
Bud or Steph, can you guys hear me all right?
Okay. My wife was that, space science was that.
All right, I see a thumbs up. Yeah. Yes. What about that? Oh, usually she's on it.
Yeah, I heard you say Fred Boyle earlier, right? Yeah. So you remember Fred?
Well, yeah, you just email.
Yeah, when I was in high school.
Yeah, great. Yeah, that's it. Yeah. Yeah, that's right. He was very.
All right. Well, we'll get moving on tonight's talk. Like I said, I'll speed it up a little bit. So it sounds like I'm fast talking. I am. But also down enough to catch up on the cool stuff. And then we'll adjourn from there. First, thank you everybody for coming today. Thank you everybody on Zoom. Thank you, Shane, for giving us awesome talk. He probably will be here afterwards selling dimes for 11 cents a piece. We got to cover his expenses somehow, right? But welcome everybody. Thank you again. We had to move a day back to Thursday, so I know it's just a little bit off this month. But welcome. I won't see you guys until after Halloween next, and so I put some fun, not necessarily spooky pictures, but over here on the left, I have my alien picture I took with my dwarf. On the right, I thought, what's more scary than a face in the sky? This was taken by Hubble. It's one of my favorite images here. See if my laser pointer works. All right. In 2015, that's pretty cool. I think that's pretty insane. But there's a lot of cool, fun, spooky stuff out there. And I went through and looked. There's a program that they run. Another club put out spooky sky assortments, witch head, ghost heads, witch's broom, a lot of ghosts. Here's your horse head, right? There's a lot of really cool things. A lot of owl stuff. There's also other assorted things, beasts, minotaurs, more ghosts, wizards, right? So like I think Chuck was asking about doing stuff on Halloween. I mean, you could point at all these and just run the gamut. I then went and talked to this is where your face is, just below the belly of the bear. So if you wanted to look at that, you're gonna need probably a good exposure to catch that. From the images I've seen, it's about the size of Saturn in the sky. But I thought that was pretty cool. Me and ChatGPT went to work, and I asked about how we doing in Nashville mid-October. And so these are things that are up kind of around the sky and accessible for us. So I'm always a fan of the the Demon Star and the clusters and things like that. So those fun things to look at. All right. That being said, we'll go ahead and call everything to order. Hopefully you guys had a chance to look over the minutes in the clips from the last month. If you have any questions regarding the happenings between now and last meeting, including board stuff? Awesome. I don't see Keith on here right now. Our member numbers, we're at 244 members, so increasing little by little. So that's pretty good. I don't see Theo as well, but I did take a screenshot of our numbers. Give me just one second. For our treasury balance, we have a total bank balance of $7,754.25. We have 3875.41 in savings, 3878.84 in checking. So that's where we get our two numbers. Expenses, we paid 1856 for our Zoom account. They've increased us about $1 a month, but it is what it is. PayPal, we have 308.55 because people pay for posters and stuff like that, memberships, and that's where that goes. Social media, Theo puts on here. Facebook's, we're now followed by 2.8, right? So that's a boost from our 2.7 that we've been on for a while. Twitter, we still kind of we haven't posted much on there. We're at 325 followers. And social media, thank you, Donna, for really getting us going on that. A couple things coming up. Our next member meeting is the third Wednesday in November, unless we get told otherwise. But I'm pretty sure it'll be next Wednesday, third Wednesday of November, November 19th. And it'll be here. We'll also have Zoom and YouTube links as long as I remember to hit the button. And it's our yearly All I Want for Christmas talk. I know Keith has been traditionally giving it. He's been putting it together. I think I got shoehorned into giving it last year. Keith conveniently had to get out of town. And so there's a good chance I'll put it together and run it with him or for him this time around. Coming up for to think about, because we have November and then in December, a few things happen. In December, our meeting is our annual potluck and our silent auction at the club. So we'll send out probably a form asking if you're interested in going to the potluck, so we know how much meat to bring and stuff like that.
It'll be up here.
Yeah, it'll be just like what's unless weather, because that hill doesn't work in the snow. Yeah.
Freezing.
Yeah. So we'll email a lot about potluck to see what your thoughts are, and just to kind of get a rough number so we know how much stuff to get. We also run a silent auction, then the money will benefit the clubs and buy equipment and things like that, stuff for star parties and outreach and things like that. So if you have anything that's just sitting in a closet and you're like, I don't need this, I don't need the money for it, feel free to donate it, and then we can auction it off here. We really appreciate those things. And then also coming up in December is elections for 2026. We currently have two board every year. from now on, we'll have 2 board positions that'll be rotating. So, and we're voting communities. So, in December, we'll have our election for next year's board. And so that'll include all of the officers that'll be voted on, and then the 2 director position, the at-large director position. So if you're interested in serving or helping out the club, reach out to us. The info at BSASNashville.com email address will get it to us, and let us know if you have any questions or if you want to help out. Let's see. Moving on, I know that we had a lot of interesting talks today, and I've seen faces that I hadn't seen before, so it's really exciting to have people here. If you're not familiar with us, this is our website. You can find us here. Again, I won't dive into my normal spiel on here like I usually do, but this is our place where you find us. This is my favorite thing on our site. I actually have my telescope imaging right now because it's nice and dark. I set up the schedule before I showed up. That's why I was in 10 minutes before the thing started. So I'm imaging right now because we had nice clear skies. Friday, Saturday, I thought we were supposed to get some weather, so potential. So I don't know how well that's gonna pan out, but just keep in mind as the weekend comes up. Over here on the left side, if you're interested in becoming a member, you're new here, you're like, I really like what we're seeing. There's amazing every day. Maybe a little bit, but if you're interested in becoming a member, you can click here and it'll take you to this website where it shows you what the perks are of becoming a member. You get the Eclipse newsletter to astronomy telescope. You get membership to Astronomical League, including you get a subscription to their newsletter, the Reflector. You get our newsletter, Sky and Telescope, astronomy discounts. So we're loading up your library. You get a vote in our BSAS elections. So you get a say in leading the club down the road, and we have private star parties that we have access to. So the rate relatively low. $25, family 35, student 15, senior and senior family 20, and this is per year. So relatively cheap. So becoming a member, you'll go through here and pay, and then we'll work you through Night Sky Network. Yeah. That is a question I am not going to answer. If you think that you're a senior, I am not going to question. I'm not going to accuse anybody of being a senior either, because I have manners. You do not look like a senior, lady. It's about the money. Yeah, I managed the accounts for a really long time around here, and I never questioned, are you really getting the senior coffee? I want to see her, we'll get it taken care of. Yeah, maybe we should put it in the bylaws. I don't know. We'll figure it out. Yeah. But relatively not so bad. Probably as much as a senior coffee now. I don't know how senior coffees are at McDonald's anymore. But if you're interested in becoming a member, you'll go to Night Sky Network with Remit. You'll create an account there because that's how we run our membership. You'll send in the PayPal. Make sure you put name, address, whatever, so we can know that you paid and that we can take it in the network. And then Keith, who's our membership director, will add you in and we'll go from there. One of the other perks of being a member is we have the loaner equipment. We have a storage unit full of telescopes now because we had a lot of people return, which is, so we've got telescopes. So if you're interested in borrowing a scope before it's always a good opportunity. If you wanted to see if you would use an 8-inch Dob, we got an 8-inch Dob. If you're interested in an SCT, we've got SCT. An SCT is, it's a great time to learn what an SCT is, right? So we've got telescopes that you could potentially borrow and use and see if you like it before actually spending money to buy it. Astronomy is one of those hobbies that will take all the money you want to throw at it. And so the best telescope there is the one that you use. And so feel free to use ours before you buy one of yours. All right. So make sure you're going to use it. The list is on our Google group. You are using one. If you have one borrowed, feel free to reach out. Let us know if you're using it, how you're using it, what you like, what you don't like. If you think it should be better, maybe there's out of collimation or something. Give us a reach out and say, hey, this is what I'm seeing. Like, yeah, it's a 4-inch scope. You're not going to see much more than that. Or you should really be able to see that something might be off with the telescope. We can work on that and see what. And so that, and if there's anything we can help with, just let us know and reach out to us, and we can get you taken care of, hopefully. There's also places that we are social, and so I'll just run through these real quick. We are on Facebook again, 2.8 thousand followers. Sweet. Thank you, Donna. Slowly climbing. We're at BSAS National on Facebook. We commonly post links from around astronomy sites we frequent. We still post pictures from our members that post them into the Google groups. This is Brad. He is also on Astrovan. Brad also made it onto Instagram. So here's his picture on Instagram. This is our Instagram feed. Again, BSAS Nashville. So it's a common theme. If you are a photographer and you like taking pictures and you want to share it, please do. Post it to Google groups. We'll snag it and throw it up on our socials. If you like Instagram and would like to be featured on Instagram, say, hey, your Instagram site, here's my handle, right? Because on Instagram, that's how we find you, and we can give you credit for your awesome pictures. So, if you want that public notoriety of BSAS brings, let us know. Okay. Just email us at info@bsasnashville.com or post it to Google Groups. Speaking of Google Groups, this is where it's at. There's a few things on here that I always point out. Here is where you'll find our equipment list. So remember, and you have access to the group, send us an email to make sure that we can get you in here. Again, this is how you can get in touch with us. The equipment list, what scopes we have. And if you're interested in one, just click I'm interested, and it'll shoot an email to our equipment people, which is me and Gene back here now. So we'll get that taken care of, and we'll probably reach out to you and be like, okay, this is what we got. Let's make this happen. On here is also our permit to Natchez Trace. Our private star parties, we get access to a couple spots on the Natchez Trace Parkway, which is our darker access points here. The Water Valley Overlook is about an hour and a half from here, depending on how you drive. But it's our darkest site we have access to. And so we have a private star party once a month. If you go out there, be sure you have a copy of the permit. You don't have to have it printed. It can be on your phone. If not, it is federal land and they will roust you after dark. So that's one of the perks of the club. Go through and get this permit every year. Also on our Google groups, we'll have pop-ups and star parties show up. So we'll talk about those in a minute, but hey, who wants to come and look at stars? So if you'll get an email saying, hey, who wants to come look at stars? And so it keeps you involved with the community. People also post a lot of pretty pictures. And so this is where we get to show some of the pretty pictures. Here's Comet Lemon a couple days ago. This is a link to Brad's Aspen. Comet Lemon's interesting. It's getting a little bit brighter. This is its trajectory as it goes through. We are somewhere here-ish. So here's the dipper, right? We're October 17th, 16th right now. And so it's slowly working its way across. This becoming a lot more steady. I think I saw somebody posted, I don't know if it was one of their images or it was a GIF. I think it was like a stack of images together where they actually caught the tail breaking off from the comet, or that little chunk coming off there. And so it's pretty cool to watch all this happen. And so I was amazed by comets, because that was actually the first thing that got me interested in the sky, was living in Texas, looking up and seeing a comet. I don't remember how old I was, but it was like, oh, this is really cool. There's a lot of cool stuff. And then Jeff posted this under Bortle 8 size, 365 hours of data collection here. it's insane the quality here. And this is this area between North American Nebula and Pelican Nebula. If you're interested in more write-up that Jeff put, if you go to that, it'll take you to this image. And when you click this image, AstroBin will go, hey, let's zoom this for you. And so that image, and I moved around and did some stuff, right? So this, I wanted to see just the detail here because I'm intrigued by this little area. And I don't know how it'll show up here, but like little filaments everywhere. I mean, there's insane detail here. And so that's what 365 hours will get you with, a lot of patience and skills. So thank you, Jeff, again for posting. Speaking of AstroBin, oh, well, this is Steve's the son he took the other day. I put this up here because check out that flare. That's a big mamma jamma. Steve mentioned it wins the award for the largest flare he's seen. It's the largest flare I've seen as well, but I haven't stared at the sun much. But that's pretty, yeah. Yeah. A lot of little things coming off there. Yeah. So it's always fun to look at. Steve, how do you like that? Have you gotten a lot of use out of your spectrograph?
Still get familiar with it, but it's
The heliograph, yeah. Yeah. So a lot of cool stuff. On our Astro, if you do pictures of star stuff, we have a AstroBin group for our club members, and so these are all images from our club. You can see that we have a lot of talented photographers in here. You don't have to be a photographer if you want to just look at pictures. You'll email when somebody posts something from our group, and so you can see how they did, what they did, what equipment they used, and things like that. So as Jeff posted his picture of the Rift, I'm like, ooh. What equipment does he have? Because I want to do that. And it's, good equipment. So it gives you targets, right? Again, astronomy will take all the money you want to throw at it. So, all right. The other thing, we're part of the Night Sky Network. That's how we run our members. If you go to this link on our homepage, right, you can click this button, join the club, have you sign up through our club. Once you sign up, we'll be saying, hey, there's an application to be approved, and we'll go through and see the PayPal, handshake, and Night Sky Network, and then we'll add you in. If you've applied and haven't heard from us, Heath might be busy. He's the one that goes through and does the membership, but give us a little bit and we'll work you through. If it's been more than a couple weeks, just reach out to us again and we'll make it through. On Night Sky Network, I always like to explore. This is the kind of their outreach page or the home page, and front and center, what Shane was talking about. They are, really going into hey, it's been 10 years since we spotted our first group of gravitational waves, and they made this cool GIF. I think it's pretty fun, right? So I managed to get it here. So this 10-year anniversary of the first time we've detected waves, and this is a little GIF that they made of how we can detect things, and so measuring the length of the laser as the mirrors change. When you go to this site, they have a whole bunch of material, or when you go to that article, they have a whole bunch of things besides this GIF. They have outreach items, and so outreach items, notice marble, laser, mirror, and a target card. And what this is, this yellow stuff is Jello. And so I went, oh, how's this? And so I took the video and GIFed it. And so here you can see they drop the ball and it creates these waves and it hits the mirror, and the light, when it bounces off, you'll see it kind of bounce around on that target. And so kind of cool. You have a lot of Jello, or you want to do stuff with kids, right? Like kids like Jello and dropping things. So I thought that was a fun way to show how these impacts work, right? So also in that link, come on. Also in that article, there's some citizen science stuff. If you're interested in helping out in the science world, there's quite a few things that you do. Here, they're looking for black holes, and they basically train you with light curves, and then you go in and you look at light curves and how they change, and you mark things that you think potential, and then other scientists more trained than just a PowerPoint presentation, I'm sure, will go through and study it and take a look at it. It's 90% complete, finding black holes. So it's interesting just to see how they're doing that. And they also had this one, Help LIGO, and this is where they're looking at their data sets and you're helping calibrate their data here, where you're helping them use their tools a little bit, right? So they can do better at detecting. So again, it falls right in line with the gravity stuff. You know anything about all these?
We wrote this one.
You wrote that one? So, Dr. Larson, how is it? Like,
Our team at Northwestern did this. So the problem is the computer looks for signals. And then if it sees something, it tells us, hey, you should go look at this. And so it gets fooled by things that aren't black holes in astrophysics, right? And so we train the computer that this isn't a black hole and this is. But we need to know what these things are. So we've done 2 million classifications with the citizens here. So for example, one of the things it found that it was being fooled by, the citizens identified, and we've talked to the computer, it's ravens pecking at the cables on the roof of the thing, right? So we discovered that people are doing a gravity spy for us. So
That's awesome.
it's very helpful, it's valuable, it's what we train computers to do, but you're right, rather than
yeah, yeah. So I promise, I had no idea that this is just fortuitous, right? But if you do spend hours upon hours with this, talk to Dr. Larson, getting paid. No. But yeah, so if you're interested in helping out the scientific world, this is how we get data and things that we can rely on. More into the Nice Guy Network. We're almost done, I promise. There's a couple cool things I always point out. Coming up in October, here's tonight. We're really close to Regulus, and then later on in the month we have our Orionids that are coming through. So if you haven't heard anything about it from the news, I'm sure we will as it gets closer. The greatest meteor shower ever that always comes out. Also on here, there's a lot of data: moon, clear sky chart, sky maps, spot the station. I always like their sky maps because they have a lot of things that they can target that are recommendations. Important events on here on the backside. They show things that you can see with the naked eye, binoculars, and telescopes. So, it's really good for just like, oh, what's out tonight? And you can go through and take a look at that. The spot the station, I use this at least once a week to see what my upcoming week will look like. If there's going to be any station crossings that I can go out and wave at the astronauts or not. And so, again, they used to have a link to your the place where you lived, and it would show you. Now they take you to a website. You can get this data. So this was yesterday when I took this picture. It was flying over Australia, heading for mountains of Mordor. And then here we have where they're pointing people now to download the app. And so they have an app on the App Store and Google Play. This is the Spot the Station app in the phone or in my on the Apple. So if you needed to download this, here's the QR code for our Apple, here's the QR code for the Google Play. This will give you notification saying, hey, the ISS is coming in 15 minutes. And then about a minute before it hits, it goes, the ISS is coming. And so you can run out your house. And it's got a augmented reality, so you can turn it on and it'll look and hopefully align where you're at so you can see where it's at. So that it's done pretty good. I'm fairly impressed with it. This is what the app looks like. There's the AR. This was tonight. I took it right before I showed it. If you click here, it'll take you to upcoming sightings. So tomorrow there's one at 5:30 in the morning. October 18th, there's 4:43. The quality of the pass, right? Like anytime you get to wave at them is awesome. But like max height, I usually have that set to 30 because I got trees and I have a horrible sky. So if it's above 30, I'm not getting out. But if you take that and lower that, you'll get more sightings. Here you can see the max height of 20 degrees. That's going to, kind of do that number. But you can basically say, I don't want anything over 30. I want longer durations than 3 minutes, right? If it's 2 minutes, I'm not getting out of bed, And so you can regulate that and get these sightings. So matching these, there's only 2 coming up, and I think the next 10 days. And so it's a really cool site. Now, because we like data that we can make a little bit more tangible, we like tables, we like charts and stuff. I started pointing people to Heaven because they have a whole bunch of stuff with satellites. Here's ISS interactive 3D visualization. You click on this, and here's the ISS when I took this picture earlier. You can drag this around, read it, zoom it around.
I like Heaven's Above. It's easy and it's just,
Yeah.
it's pretty.
Yeah. So if you like dealing stuff on the website, here's this awesome site. And so I started playing around with this. Here's our ISS predictions for the next 10 days. Comes up with this little table. Now here, visible, yes, that'd be great. But you can see when it starts, where it's highest, where it ends. And so the highest point, notice 14, that's going to be low for me. 47, that might be all right. But this 80 is the one that I got alerted for at early in the morning, right? And I was like, that's a good sighting, but I don't want to get up. I started looking around at things and I started clicking on this, and look at this path. Comes right through here and goes right below the Big Dipper. Right? Now, my brain went, where have I seen the Big Dipper already in this presentation? And I went, oh yeah, the comets, right? So I went through and I clicked on that, and it goes to Comet Finder. And so this is at 60 degrees of field of view. Here's our Big Dipper. Here's our comet limit. And then you can click on that, and that also gives you a 10-degree view. And so here's our little comet tucked in here. And so me being preoccupied with things all the time, I went, how close is this comet going to be to the ISS passing? And so if anything, I'm I do some weird things, right? You click on the graph and it'll take you to wherever you click and it'll zoom in, right? And then I was interested in this, right? So if I click here, it'll give me this zoom and it'll show me all the little stars in here, right? And I can look at that, and that's my path, and it gives me time points at 10-second intervals, right? And then I went to this, my zoomed in comet, and I played find the pattern and did this, right? And so there's my comet. There's my path to my ISS. There's my comet. And so if I'm interested in getting up early in the morning, I'm right there. So seems like it'd be pretty cool to catch that going through. Yeah. Oh, see, did you see the ISS? Yeah. Might not be that big. If it's that big, we probably got a problem.
But it was minus 3.8 magnitude.
Yeah.
It's going to be super bright.
Yeah. So it might be worth getting up and looking out the window at 5:32 or setting up my camera equipment at 5:29 and just letting it go, because that seems like it'd be pretty cool. Now, I'm not obviously the only person to think about ever doing this. This image was from NeoWise with the ISS. So there's NeoWise ISS. Hard to beat this image, though, being on the ISS and capturing Lovejoy, right? Like, can't get that, but still, again, there's a lot of stuff out there in the universe that makes things interesting, right? All right, past events and outreach, we're almost done. We had a lot of things going on last month in terms of stuff being posted on Google Groups. We had stuff at Lebanon, Henry Horton, Hidden Lake. We had Chuck doing STEM night with Tony. Thanks, guys, for doing that. How many kids did you guys see? 2. That tracks. But thanks for going out there. Thanks for going out and doing that. Bowie, we had a good turnout there. Shelby Bottoms, I believe, another good turnout there for International Observer the Moon Night. Things coming up. We have a private star party scheduled for Saturday night out at Water Valley. Again, I'm going out. The permits on Google Groups. Send a message, say like, hey, I'm thinking about going out. Anybody else want to go out? I haven't seen a bear out there, but it's always good, having people out there with you. I haven't heard. I don't mind sitting out there watching for bears. But so we have that coming up on the 18th, and then we have a public star party next on the 25th at Bell's Bend.
That's it.
It's Warner Park. Is my data didn't change? It's Warner Park. It's Warner Park. I'll change it. I'll make sure. But then on the Google groups, we have posting Cedars of Lebanon, Montgomery Bell State Park rescheduled from the 3rd, right? Yeah, So Chuck's running that. If you have any questions, then there's events even showing up for November in the Google group. So reach out there if you have any questions. And then finally, next member meeting. Again, just to rehash, November 19th. So it's next month, 3rd Wednesday, 7 p.m. All I want for Christmas, hopefully here, unless we got a snowstorm for Thanksgiving. So, all right.
Can I mention the?
Yeah. Oh, yeah. So next month we're thinking about having an auction. So Chuck, go through it.
Yeah, Ms. Tyler has some telescopes and some other gear, and what we would like to do is have just a quick auction right here during the meeting. Maybe a couple of Dobsonians, I think you said there were a couple.
Yeah.
And we'll get a list together.
There's gonna be at least one, maybe two Dobsonians, and then there's like 5 others.
So I have several telescopes. We'll get a list out on
And it's
BSAS, Nashville, and
Yeah.
I guess maybe try.
Yeah.
Fit.
We'll do so.
We'll figure out the logistics of it.
Yeah, we'll send out an email when we get closer to the next month's meeting. If we can get a list of the things, and we're gonna have a minimum bid. So we're not gonna go by a dollar, like $10, $20, right? Like we'll say, all right, minimum here, and we'll make sure that we'll
Cash and check. So
cash and check if you can. So
you said all you want for Christmas, right?
yeah, so you can work on your list.
Yeah.
Yeah, if you show me in advance, I can add them to my program. But all right, any unfinished business, Tony? Yeah.
There's.
Okay.
They're all bubble images, from NASA.
Perfect.
We've got a whole lot more. I brought some in. Papers you want.
Good deal.
Rather than-
Free Hubble images. Everybody loves Hubble. Not from this Hubble, the big Hubble he showed on the real Hubble. All right. Any other, Steve?
Just FYI, that big scope up to upstairs on Saturday. Come out and see it.
Yeah, check out the ears on Saturn. All right. Anything else?
The first thing I lose through.
All right. Well, thank you everybody for coming. Have a good, safe month, and hopefully see you at Star Parties in next month. Take care, guys.
Thank you.
Just before.
Yeah, wow.
My parents gone.
I really enjoyed it. Thank you.